Hello, today I will be talking to you about the basics of photothermal heterodyne imaging. We'll go over some basic terminology first. The photothermal effect is a phenomenon that occurs when electromagnetic radiation, such as light, interacts with a material and produces thermal energy or heat. Pretty simple. Heterodyning is a type of signal processing technique in which a new frequency is created by combining or mixing two frequencies. To illustrate the basic principle, imagine a setup that involves two different beams of light. One, a signal beam, and the other, a reference beam known as a local oscillator, or LO. The two beams are combined by a beam splitter and detected by a photodiode. When two beams with different optical frequencies are superimposed, they form a beat note, which is a signal with the difference of the optical frequencies. The photodiode then measures the optical intensity of the beat note. Photothermal imaging is primarily used to examine non-fluorescent objects, such as gold nanoparticles, which are difficult to detect optically when their size is much smaller than optical wavelengths. The first thing that needs to be understood in order to talk about photothermal imaging is plasmon resonance. When light is incident on a metal nanoparticle and the frequency of light matches the natural resonance frequency of the particle, it will produce large oscillations of all the free electrons in the metal, which then produce large electric fields in the immediate vicinity of the particle. These fields then act on the electrons, reinforcing the oscillations. This coupled excitation of oscillating charges inside the particle and oscillating electromagnetic fields outside the particle is known as plasmon resonance. After excitation, the plasmon relaxes through two channels: radiative decay, or scattering, and non-radiative decay, or absorption. Extinction refers to the sum of these two processes and represents the total amount of incident light removed by the nanoparticle. The balance between these two processes can be modified by altering the metal nanoparticle's shape, environment, or composition, and can be optimized to favor one property over another, and thus one application over another. Metal nanoparticles scatter light efficiently, allowing radiative properties to be easily isolated from their net optical response on a single particle level. And there are many techniques that characterize scattering. Recording pure absorption of single nanoparticles is more difficult, however, primarily because the signal from a single nano object is typically too small to be measured against the high background signal, and increasing the size of the object to enhance absorption also increases the scattering cross-section, which then greatly overwhelms the absorption cross-section. One way around this difficulty is to use a thermal intermediate to measure absorption. When a small nanoparticle is embedded in a homogeneous medium, such as water or glycerol, shown in blue, and illuminated with a modulated heating beam, shown in green, it behaves like a heat point source and absorbs energy from the heating beam, exciting electrons in the nanoparticle. The electrons then relax non-radiatively and lose almost all of the absorbed energy as heat to the nanoparticle's immediate surroundings, causing the temperature of the surroundings to increase locally and creating a temperature gradient around the particle, shown as concentric red circles. Since the refractive index of the embedding medium is temperature dependent, an increase in temperature causes a decrease in the local refractive index and thereby creates a corresponding refractive index gradient. The probe beam, shown in red, is then scattered by a change in refractive index and results in the photothermal signal, thus allowing for pure absorption information of individual nanoparticles with sizes of only a few nanometers to be detected. A basic photothermal setup consists of a probe or heating laser with a wavelength that is in resonance with the surface plasmon resonance of the particles of interest, and a second non-resonant laser as the probe beam. The two beams are overlapped with a beam splitter, and the overlapped beams are then directed onto the sample through a microscope objective. The heating beam is absorbed by the particle, and the probe beam is scattered and frequency shifted by the change in refractive index. The scattered field of the probe beam is then detected by a second microscope objective and collected on a photodiode through its beat note with either the reflected or transmitted probe field. The signal is then directed to a lock-in amplifier to recover the photothermal heterodyne signal, resulting in an image that looks like this, where each point or dot represents a single nanostructure and its corresponding temperature and refractive index profile. And there we have the basics of photothermal heterodyne imaging.